Okay. This actually comes from, I'm doing this O'Reilly video series, and I think some people here like did the online class back there. I think the next one's coming up in, is it Friday or Saturday? Or no, yeah, it's in a couple weeks, I think. Yes, I have one personally that's actually on Saturday that I'm going to be broadcasting from like London from my hotel room, which is that like goofy boat that's right outside the Excel Center, the Sunborn thing. There's gold, like there's mirrors everywhere, and then gold fixtures, and it's like I feel like there's a dual purpose for this boat when Strata is not in session. But yeah, there's some weird things happening in that boat, and I'm now part of it. So I'm Chris Fregley. Oh yeah, so like the name of this video series is High Performance TensorFlow in production, right? Like technically. Right, like production means like different things to different people, right? Like production, to me, is more the real-time sort of prediction, right? Like user request response path. To traditional batch type people making batch predictions, production is just pushing it, just kind of pointing it at like an S3 bucket or something, right? So yes, either way, you're still making predictions. You still want them to be done like relatively quickly. So, but for the most part, I'll be talking about the sort of like request response type of predictions. Yeah, one of my groupies back in San Francisco, I run this like meetup out there. Actually, this is the same chapter here, but showed up with these little stickers, yeah, which is super creepy. Of course, I have like 500 of them in my bag if anyone wants them. But I guess it looks like me. All right, so real quick, former Netflix, former Databricks. Yeah, Matt and I talk a lot about Databricks, very openly, very candidly. He actually knows a lot more going on there than I do these days. It's been a couple years since I was there, so sounds like they're like making some good like headway with their notebook product, and possibly some cool announcements coming up about some of their more high performance stuff for specialized hardware. Just kind of leave it at that. Netflix was fun. That's why I moved from Chicago to San Francisco, was to get the high scale. I wasn't really getting it in Chicago, and yes, I always get crap for saying that from my Chicago friends, but it's a reality. So yeah, that's the meetup. This is, I guess, why you guys are here. You guys are software engineers, data scientists, data analysts. You want to know more about TensorFlow. How does it interact with GPUs? Should I be using GPUs? Is it really financially, really doesn't make sense? Sounds like the guys here have actually had some problems, like trying to fully utilize these GPUs, and you sort of look at like the numbers that are posted by Google, and then you go back to your own data centers or your own cloud, and yeah, suddenly it's not as like linearly scalable as. Yes, I will mention, right, like one thing about that, like Google just released their like benchmark results, but it's not just benchmark results, but also all the scripts that they use to generate those benchmarks. And what you see in there, if you start digging around some of the .py files, is that they actually have comments in there like where their queues, right, like this like queuing subsystem that like we'll talk about here, sort of streamline batches and like saturate GPUs and saturate CPUs, that didn't even keep up, and that wasn't good enough for these huge like data sets that they were running through, right, like tons and tons of images. So like you start seeing some of the tricks that they haven't really opened. Well, yeah, right. They are open source, right, because they just released them, but it sort of hacks around the existing APIs that we all know. So those are definitely worth looking into, not just the results, like I said, but actually the scripts and the code and all that stuff behind it. So we'll talk about some of that here. Yeah, by the way, this is a 4-hour talk that I'm cramming into as much time as I can. I'm going to give a modified version of this tomorrow at Strata. This is also a lot of what the workshop content is too. The workshop has a lot of hands-on stuff, so it's pretty cool. We actually do like CUDA, right, like low-level CUDA coding. We do Numba, right? Yeah, so if you guys don't know about Numba, you should check it out. It's by like the Anaconda guys. And you can sort of turn on like JIT compiling for the GPUs, and it'll generate kernels behind the scenes with just these simple, like small little annotations around your Python methods. Yeah, so, and like this is all open source stuff too. I'll show the repo here in a sec, but yeah, like you guys can pull down all of the same notebooks that like we use for the workshops. So half of this talk will be about sort of training optimizations, things you can do at like training time to speed up things and to converge quicker, and things like batch normalization, and just like tons of fun topics around training. But I do emphasize the sort of deployment and the inference, the like prediction side of things, because I feel like a lot of people don't cover that stuff. And yes, as you can see, like training is kind of typically the boring batch stuff. You're pointing to an S3 bucket or pointing to HDFS. If it breaks, like people don't really care that much, like for the most part. And it's sort of the number of like data scientists or the number of researchers that are actually trying to build models, versus like the inference side, which is all of hotels.com, like users and Expedia. And yeah, there's a lot of fun like real-time challenges there and sort of high availability and things like that. So I've been combining a lot of my Netflix experience in to the pipeline IO stuff that we're doing. So things like circuit breakers and yeah. So these were lots of challenges that the machine learning groups and like data science groups at these bigger companies like Uber and like Netflix, they all struggle with this problem, is actually deploying these models. So we'll talk about some things. There's this thing called the graph transform tool. So the first part's going to be sort of training and then training a model, or like getting it out there, and then second part's going to be so there's this trained binary, right? Like now what can we do to this thing to simplify it and kind of simplify the graph, and do things like the 8-bit quantization and that kind of fun stuff to sort of make those like prediction like calculations a lot simpler. So yeah, this is the repo here. This is everything. I had a lot of London people. Like there's this cool tool. I keep meaning to put up the URL. You can point it to any GitHub repo, and it'll scrape all of the stargazers and all the forkers and all that kind of stuff, and then it'll plot out the actual map. And kind of show you like worldwide what's going on with really any given repo. So yeah, I had fun with that. All the Docker images are out here. The one that you want to pay attention to is this GPU.ml. This is the one I was building last night with the latest and greatest TensorFlow code. Takes about 8 hours, 9 hours, and then it crapped out about 6 a.m. this morning, and I'm stuck on a build from about a month ago. So, but yeah, whenever they release, so 1.2-RC0 just dropped, and like the second they drop a new release, all of a sudden there's all these bugs about compiling and installations, and they keep changing all the scripts, so it's kind of hard. I'm going to be doing this is going to be show and tell, and this is experimental stuff. Like we're going to talk about things like the XLA framework, the Accelerated Linear Algebra framework, which if you're familiar with Spark, it's similar to the like operator fusing and like Project Tungsten. It's more so the second generation of Project Tungsten, right? Like the first generation Tungsten, which was like Spark 1.5.1.6, was just to keep Spark from being shitty, and Spark 2.0's Tungsten was more to like take it to the next level. So Spark 2.0's Tungsten, for example, can like dynamically break apart your logical plan and physically create like Java classes on the fly and Java snippets. So it uses this project called Project Genino, and it can take any string, which you can generate from your like logical plan and fuse together, a bunch of maps and filters, and so that you're not making virtual function calls and all that. So yeah, we're going to cover a lot. We'll cover so there's this JIT compiler thing that you can sort of allocate. So similar to how you can allocate in TensorFlow, you can explicitly say CPU, GPU. Like you can also now say like XLA and then underscore CPU, GPU, right? So that's the actual device. And that's kind of a hint to say from this scope down, so try to fuse things together, try to apply some of these like optimizations. So that's both at training time, and then we'll talk about the AOT, which is the ahead of time compiler, which is after you've trained the model, it's now sitting there. Point to it, like tell it which nodes are the inputs, which nodes are the outputs, and have TensorFlow go through and figure out the bare minimum. And it's not bare minimum just on the graph, but it's all the runtime components. It's the operating system kernel, It's just the pieces from TensorFlow runtime to actually get you from the inputs to the outputs. So the actual TensorFlow runtime itself, I think, is like 30 meg or something. It's not huge, but if you're trying to get these on super small embedded devices and cameras and things like that, I've seen models go from 40 meg, 50 meg down to like 600K. So this is huge by just having it just kind of traverse through the graph and figure out. And the output of that AOT compiler is an actual CC library, and it's got the so it has an object file, has a header file, things like that. I picked this goofy Peanuts thing. Oh yeah, did you guys see Peanuts just got sold or bought, or there's a hostile takeover? I think it was some Canadian company or something, which is totally crazy. Everyone does not get a GPU today, but I figured I'd keep this in just to make you guys jealous. I do want to thank Google. Right when those guys came out with the GPUs, I actually I was at the conference with Matt, and I was working a deal with those guys to be able to use their new GPUs for the workshop and for big conferences. So they gave me huge quotas, 250, things like that. One thing I'll mention that's pretty important actually, and I got burned by this at the PyData London conference a couple weeks ago. I spun up a huge cluster in the EU West, and I didn't even think twice. But I got allocated on CPUs that didn't have AVX and some of those vectorization, Intel optimizations. And when you compile TensorFlow from source, you can say, turn all that shit on. And I had turned it on because in the US West and US East and all the US regions, I just never got that bad luck. But yeah, so literally 250 instances came up, or I think 280 came up, and not a single one was usable from a TensorFlow standpoint. I think people were setting up, Minecraft servers and things like that, but yeah, definitely didn't do any TensorFlow that day. So there's this risk, and actually we saw this the early days with Amazon at Netflix, where we would occasionally get brought up on an AMD Opteron or whatever, not the Intel chip, so not the actual hardware that our benchmarks were all based on, and all of our debugging tools and things like that. And this was back when we were a big customer for Amazon, but didn't have a lot of the pull that they do now. And I think that Amazon even has private clouds now for bigger companies. And so what we did was actually when that EC2 instance started up, so picture auto scaling, 5,000 instances, we'd get about 10%, I think maybe 5 to 10% that were these shitty Opterons or Optimums or whatever they were. So yeah, we would actually, upon startup, we had a script that would detect if it was the shitty hardware, and it would just kill itself. And we just kept doing this until we got 5,000. Didn't happen, it's a complete and total waste of money, but yeah, so thank you for your $8.99 or whatever that you guys pay. Yeah, actually I was part of the Netflix release out here. It's pretty fun. And we had this big party at the office, and there's this place called the Brit, this shitty bar that's in San Jose, and they hosted it. It was not, it was all the stereotypical beers and things like that. All right, so some things that are in this GPU and so this is all based on that same Docker image that's back here. So yeah, essentially these instances start up, and then and it's got Spark on there. It has TensorFlow, HDFS. So I've sort of got that whole workflow where you can do your feature engineering with Spark, sort of do the boring ETL, and then stick it onto HDFS, and then spin up an HDFS distributed cluster and train that way. So one thing to note is that Tensor Board can communicate with HDFS, which is really important when you're doing sort of large multi-node training operations, and you want to write somewhere central and point Tensor Board to one parent directory, and it'll actually show you all the runs and combine everything. Yeah, before people were writing all these rsync scripts and all kinds of craziness for the distributed case, but yeah, Tensor Board. Yeah, this is one of those cases where Google kind of came out of their lab-like environment, their sort of internal environment, and they were like, oh yeah, we should probably support HDFS and like a lot of stuff that we created, or the papers that we wrote. It's funny talking to those guys because like they don't really know Zookeeper, but like of course they know Chubby, and of course they invented all this shit. They just haven't been in the open source world anytime recent. So, but yeah, TensorBoard supports it. TensorFlow Serving now supports it too. So this is important. So you can have a huge fleet of TensorFlow Serving where like nodes come up and get like you don't have to do all these goofy tricks with like Amazon EFS and hope that stuff works. You can just reuse your existing HDFS clusters to deploy one model and have them all spin up on the same version through HDFS. That just came like a couple weeks ago. Right. I just got back from the GPU Tech Conference. If you guys haven't been, it's probably the greatest conference ever known to man. So yeah, there's like 10 different tracks going on. It was just in San Jose. I think it's coming up in like London or maybe Munich or something like pretty soon. But one thing that like did come out this time was the new Volta. So we were just getting used to and starting to get envious of people that are starting to use the P100s that had come out at like the last year's GTC conference, and now they have Volta. So Volta expands, it's got, I think, roughly the same number of cores, actually, but it's got these new these Tensor Cores. Actually, I'll talk about this in like the next slide here, but both of these chips support flexible FP32. So what you can do is do half precision, right? And there's native support for this. So yeah, half precision is like all the rage now. Yes, FP16, int 8. Right, like because a lot of this deep learning stuff is a little bit fuzzy anyway, we can get away with sort of lowering precision. And these flexible floating point 32 GPU cores, there's 4,000 or 5,000 of them, whatever. You can actually slam in two FP16s and then operate on them both. So pretty much doubling your throughput if you're coding properly. I do have a slide on. Yeah, I was going to mention something else, but we'll get to it. Yeah, so this was actually announced last week. They have these Tensor Cores now, and so there's 8 per streaming multiprocessor. If you guys rightly don't know, yes, people always talk about cores, right? But actually, the streaming multiprocessors are sort of like logical groupings of these things, and off of the actual manufacturing line, like all of these cards have the exact same number of SMs. It's just they just disable them, right, for the gamers and so it's just a classic manufacturing trick. But yeah, you'll hear people talk about SMs, and yeah, that's what like you want to pay attention to. So, but yeah, so there's 8 of these Tensor Cores per streaming multiprocessor. You can now with the V100 do floating point 16 and floating point 32 and like mix them. There's a sort of the right and the middle is kind of you're doing some operations in FP16, and then you've got FP32 coming from somewhere else. Think of like a matrix multiply being combined with an add, linear regression kind of thing. You can mix and match now. Let's see. Yeah, a whole ton of like teraflops. I've stopped paying attention to teraflops. It's awesome. It's just there's so many. I'm like, all right, that's a shit ton of teraflops here. The cool thing though is because of these like Tensor Cores. Right, like the actual inference throughput is now like much better. So these Tensor Cores are similar to the Google TPUs. They kept these really quiet until the last minute, but yeah, they're optimized for forward power, right? For just big huge matrix multiplies. The V100 also has more shared memory, right, which is always good. First time we see the L0 instruction cache. And bigger L1 data cache. I do want to mention CUDA 9 is also coming out, and there's a huge paradigm shift here. If you've done any CUDA programming, it's completely barbaric, and kind of reminds you of when you were first learning C and hated life, and you were coding defensively, and you're always checking for errors, things like that. With CUDA 9 now. So there's this new independent thread scheduler. So this is more similar to like traditional CPU like programming, right? If you were doing a lot of CPU like threading and what's the famous book, the like concurrency in practice, Java concurrency in practice or whatever. When you switch over to CUDA, you have to sort of unlearn all that stuff and just like plow as much through as you can. SIMT is what they call it, the same instruction multiple thread. You're just trying to vectorize and just trying to do the same instruction. If you do have branches in CUDA 8 and before, this was a nightmare. You had cores that were being not utilized, because that same instruction has to be run, and if it's not supposed to run on a particular like set of threads, then those cores just sit idle until they can reconverge. It's this sort of diverge and then like converge concept. So now you have more control. You can actually do the explicit synchronization. They say just short enough to pull anything out of there. This is not going to end well, is it? So check that out. Because CUDA has been so barbaric, I always make this joke that like the NVIDIA guys spend so much time building these profilers and debuggers and all kinds of ways to figure out how shitty your code is and tell you what you should be doing versus just changing the programming model. And so this is kind of the best of both worlds now with CUDA 9. Like we've got more familiar threading semantics, and we still have all these goofy profilers and stuff. I'm actually going to show in TensorFlow, there's a couple lines of code. Not many people know about this. You can instrument Azure training. It'll generate this big JSON file that you can then pull up inside of the Google Web Tracing Framework, or WGF, which I've successfully avoided my entire career because I don't do too much web development. But they've repurposed that tool so that within Chrome you can actually pull up and profile and see where are your operations spending the most time and which GPUs are involved, and you can actually see the utilization. And you can see when you do get something that's JIT compiled, you can actually see it change. So I'll show a before and after, where before there's a bunch of functions or operations, what they're called in TensorFlow land. And then you see after they've been fused together, and that's great from a memory management standpoint, right? You're not constantly pulling memory in and then clearing the caches and and then pulling that data back into the registers for each operation because you fuse them together. So one thing I'm going to mention too. This is all kind of leading up to how TensorFlow uses CUDA. CUDA streams. CUDA streams have been around, since CUDA 5, CUDA 6, I think. And I can't even imagine a world without streams, but it's just kind of interesting to highlight that this actually did not exist for a while. When it didn't exist, what would happen is the GPU basically can only do one thing at a time. It could either process or it could do the I/O. And this is very important when you're trying to move data between CPUs and GPUs because it is kind of a slower bus. Now with streams, you can actually sort of synchronize at a stream level, and it can in the background start to pull in data. This is the basis and the reason why TensorFlow has this queuing sort of infrastructure that we'll talk about heavily here in a bit. And the whole goal is to just saturate the GPUs with GPU stuff and not have it spending a lot of time doing I/O and some of the stuff that could be best done on a CPU. So we'll get to this here in a bit. All right. Who here actually uses TensorFlow on a day-to-day? Yeah. This is, sorry? Oh, yeah, Watson, right on. It's so funny, this is exactly, when I used to do a lot of Spark talks, it was the exact same thing. There would be 2 or 3 people using Spark, and then a year later, everyone's using Spark. So. some of the terms here, I'm not going to go through all these, but, and this is something I've talked to the Google guys about at length, is sort of their terminology and the documentation and their talks. Yes, as you can imagine, Google is huge, and they don't use a lot of the same terms from the research side, people writing the papers, to the evangelists, the developer advocates, to the people writing the samples. And so here's kind of the canonical terms here. And there's a couple I really want to highlight. There's these things called feeds that are in the lower right. And so this is just typical linear regression here, very simple. Oh yes, I should have mentioned that, is that I'm going to use a lot of simple models, and that's mainly so I can focus on the other stuff and not get bogged down with convolutions and max pooling and all that stuff. I just want to focus on how does TensorFlow do stuff and sort of best practices. So you'll see, people call these placeholders. That's what it's called in the code. You'll have some people call them variables, which isn't the right term for a feed. There's a lot of different terms. So just ignore all that crap and just think that you're feeding data into this graph, right? And it's a similar graph to how Spark does it. It builds up this directed acyclic graph instead of sort of SQL-like things like maps and filters. These are numerical graphs, and you feed data in, and those go into what's called placeholders, right? But again, if you try to learn all these terms at one time, it's very confusing. But when this graph is built, you put this placeholder in place, and it's expected that you feed data in. So if you always think of feeds, and then the opposite is fetches. So fetches, yes, I mentioned earlier about inputs and outputs, and you can have TensorFlow figure out from a given input to the specified output, what's the minimal. So yeah, that's what I'm talking about here, is these feeds and fetches. What's confusing is that fetches usually come from operations. You fetch from an add operation. Typically, when you think of outputs, you think of it, being pulled from a variable, which would be probably closer to the user feeds. Oh, so I've got user as sort of the actor that's doing these things. TensorFlow is training variables. So the term variable is super generic, but that's the actual term in the code for what you're trying to learn. You're typically, and they're sometimes called weights, parameters. What's really confusing is distributed TensorFlow, and most distributed neural networks have this concept of a parameter server, which is kind of this sort of separate cluster, that's it's typically CPUs because you're just storing data. So yeah, you're training these variables, and tensors are flowing, right? So tensors, I should probably start at the top on that one. Yes, any n-dimensional array, right? Even scalars are considered tensors. You'll hear a lot of talk about devices. This is what I was saying earlier. In your code, you could actually specify, and this is the Python code, to do it. You say, put this block of code that's coming, there should be a colon after that, and then goofy Python indenting, right? And yes, anything indented within there will get placed onto either of those two GPUs. So actually this is the same, this is one GPU but on two different workers. So yeah, this is actually the distributed case here. But yeah, so you can actually explicitly say CPU, you can explicitly say GPU. If you don't specify anything, so TensorFlow will sort of make good decisions. It'll start to track heuristics, figure out, and typically, if you have a multi-GPU system, right? So you have one box with 16 GPUs, it's typically going to pick one, right? Which is kind of counterintuitive, but it's that same sort of argument. People always want tons and tons of Spark workers, for example, but you forget then that there's a lot of inter-worker communication. And it's the same way on a board, single board with one CPU and 16 GPUs. There's got to be a lot of inter-GPU communication and things like that. So let's see. You typically only ever specify CPU colon 0, which would be all the CPUs. You can actually target one specific, so if you have 8, you can say, put this on one CPU. I've never seen anyone do it. I don't really see a reason for it. You do typically specify the GPU number. So GPU 0, GPU 16, or yeah, 15, that kind of thing. And then also, this is where the XLA stuff comes into play. So you could say not only put it on the CPUs or a specific GPU, but also try to JIT compile it. And like you can do this at the entire like program scope, or you could do it, like a with kind of thing, where we're placing it onto a device. You can even get even more fine-grained and put with JIT scope, and that's within a device. Super fine-grained, just a couple lines, things like that. Tensor board. This is actually one of the, so there's always a few reasons why, these technologies start to pick up. And with Spark, for example, it was a lot of samples, a lot of demos. They crammed in machine learning. They, crammed in graph, right? And people were just naturally kind of intrigued by all this stuff. So, and of course, the performance benefits over the typical like MapReduce, like Hadoop scenario. But so this is actually one of the reasons I think TensorFlow has pretty good traction, is that it has sort of metrics built in. Like from the beginning, this doesn't necessarily solve that problem of what is my network learning, right? That like age-old thing that kind of holds these neural networks back every 10, 15 years, whatever. It's like really difficult to explain what's going on. But this does show you in real time, and so like I said, distributed, how well is my training going? And if you are also validating your models, right? So typically you have like one cluster. This is at scale, this is the thing, but you would have one cluster that's just constantly training, and then checkpointing, right? And when you checkpoint, you're just saving out those weights, right? Those like variables, and at the same, and so every hour when you checkpoint, you spin up this separate cluster, right? That's doing validation, and it's just literally picking up, right, like the most recent checkpoint, and then spinning up and then validating. And then if your training is starting to show signs of like overfitting and not doing well on this kind of holdout validation set, then you would want to stop the training, change some of the hyperparameters, change learning rate, change actual architecture, right? Yes, this is kind of interesting, is for these neural networks, the actual architecture, that graph is a hyperparameter, right? Like that's one of the things that you're tuning. That's one of the things that you have control over. It's kind of a complex one to reason through, but just do it the old Google way, spin up like 10,000 GPUs, and you can find out within a couple hours if it's the right architecture or not. The way it does it, you have to actually instrument your code. I think Keras and some of these higher level like APIs have made this a lot simpler. This is bare bones like TensorFlow, but it's physically writing these event files, which is just kind of their own format, and then TensorBoard knows how to read them and render them. And it's not a huge team at Google that builds this, but they are pretty badass, and they're given freedom to kind of take in feedback from the community. Yes, I also know a couple companies that have spun up around these event files, and Google is making TensorBoard more of a pluggable framework. So you can actually have your own tabs in there, and you can do things with these event files. One specific use case I can think of is this guy was frustrated that he couldn't get GPU metrics, right? And yeah, he can see CPU metrics, things like that, top and all that. So yeah, he's actually scraping the NVIDIA-SMI every half second or something, and then combining that with the events, sort of file format, and then he has a tab up on top, which is really cool. So during training, you can actually see, are my GPUs being utilized, which right now is a tricky thing. The age-old question, all right, TensorFlow is great. How do I use this on my existing Hadoop data? How do I use this with HDFS? How do I use this with Spark? I get asked this question all the time. The best success that I've seen in this regard is kind of keep the clusters separate, keep your Spark clusters separate, keep your MapReduce clusters separate. Right, there's these frameworks like Tensor Frames that came out of an old company, Databricks, that are kind of half like developed. Yeah, they might be doing some stuff internally, proprietary. I don't know what's going on these days with that particular framework. But if you kind of keep these clusters separate, right? Like keep in mind, TensorFlow is distributed if you're using it properly, right? If you're using single node TensorFlow, there's really no point, right? Like Google didn't create this for like single node use case, which is actually why when TensorFlow first came out, like they got a bunch of crap for not being as performant as Caffe and like Theano and things like that. It's because the system wasn't designed for single node like those other systems, right? It was designed for this like distributed case. They quickly fixed a lot of the issues. One thing that was there very early was the actual auto differentiation, which is the whole basis of these neural networks. The ability to do the forward pass, see how far off you are from the actual answer. From that training data, and then back propagate and figure out which nodes actually contributed to that poor answer, and then make small adjustments and sort of individual adjustments. That's the auto differentiation part of it. That was actually being done in Python, and they quickly rewrote that and put it all in C++. And there's still quite a bit of rumors out there that it's still in Python, and it's definitely not. All right, so. Yeah, there's this ecosystem project that when I first heard about this, I thought it was actually kind of a third party and wasn't going to be supported. But this is actually top level right off TensorFlow at the same level as TensorBoard and TensorFlow Serving and that kind of stuff. So this is this is what you would use in your Spark program, for example. And what you're doing is doing ETL, doing feature generation off of CSVs and off of log files, or like whatever you have. And then doing ETL into the TensorFlow TF record, right? So TensorFlow, just like sequence files, when like Hadoop first came on the scene, they all kind of have their own formats. The TensorFlow version is called TF record. There's also kind of a slightly higher level framework now. It's I think it's TF example, which is a horrible name because it's so generic. But when Google and TensorFlow talks about like the example framework, it's not like a bunch of demos. It's actually the name of like a very important class within TensorFlow, which is a row or an image or it's like an instance, like a training instance. And they have this concept of features, and they have a way to group features. But yeah, TF record is what you want to pay attention to. All right, this is a busy slide. I'm just going to summarize. If you're using feed_dict, which I'm sure like a lot of you, if you pull down some of the demos and run some of the Python code, you see feed_dict. And if you're using TensorFlow in real production, you should not be using feed_dict. Not the current version anyway. From what I hear, Google's actually rewriting feed_dict to keep it as simple as it is, but be slightly more optimized behind the scenes. So, like this actually kind of reminds me of when you were first doing Spark and you discovered the collect method, and you're like, oh, collect is the greatest thing in the world. I could debug, I can actually see what's going on after every stage. And of course, the first time that you go to deploy that same program that was working fine locally out into like a huge cluster, you're calling collect, which is pulling all the data down to one single node, which is bad in the distributed sense. So yeah, feed_dict is doing a lot of C++ to Python pickling and serialization, that kind of stuff, bad. Feed_dict is also single-threaded. What you want are, there's this sort of queuing subsystem. And it's important to point out that it's not queues in the traditional sense, the computer science queue. Well, it is, but there's way more to their queuing subsystem than just kind of a logical FIFO queue. It's actually this sort of whole pre-processing framework, and this is actually like when I mentioned the benchmarks that were released recently, the benchmark code and the results. Yeah, this is an area where this wasn't even good enough for the throughput that like Google was using to scale. But these queues, think of this other cluster now, right? So we have a cluster for parameter servers, which is maintaining variables. We have our distributed TensorFlow cluster. It's actually doing the compute. And now there's this other cluster of these queues that are not just reading data, right, like from HDFS or from file system, but like also capable of doing sort of pre-processing pipeline stuff. So the like typical use case here is you pull in an image, you crop it, you change the background color, you like make some small adjustments. What you're trying to do is show the network different views of that same image. So if you have 5 different like techniques of pre-processing one single image, then basically multiplying your training data, the examples, by 5. This will also do shuffling, right, which is really important because we're doing like stochastic mini-batch gradient descent. For the most part, you want that sort of randomness, right? Like you don't want to put data in, not unless you're probably doing time series, in which case you do want data to go in the same way it was generated. You don't want to sort of artificially introduce patterns that this network will pick up that don't really add to the accuracy, the predictive power of this model. So yeah, there's a native queue called the shuffle queue, and it's just one line of code that you change, and it will do the shuffling for you. And yeah, like there's all kinds of knobs you can tune as to how big the queue size is. Of course, seeds and all kinds of things that come with typical random stuff here. Also, queues are typically CPU. You don't want your GPUs doing this kind of dirty work. This is just simple stuff, just kind of image manipulation, things like that. Shuffling, this is not something GPUs should be used for. So typically there's large clusters of CPUs with huge amounts of RAM and tons of CPU cores, and you would size it up accordingly. And then on the sort of like retrieving side, now these GPUs using CUDA streams and this sort of asynchronous processing, it can each GPU can be operating and computing on its current batch, and at the same time in the background pulling from this queuing mechanism, so that next batch is available right when it's done with the current batch. If CUDA streams were not there, that would be bound by sort of synchronous processing, and that's no good. So keep your GPU saturated. This is actually one of the things I think the hotels.com people might want to look into. Make sure that if you're using TensorFlow and you're not seeing that sort of linear scalability, check out those benchmarks, that code, and see maybe they're doing something. Because you guys have a lot of images too, right? I'm going to skip over here. It's basically what I just said. This pre-processing can also handle that classic small files issue, right, that everyone deals with HDFS. You can have these queue CPU, just out there pulling in and then combining and then creating TF records, which are very natural to TensorFlow. So it's just capacity planning. All right, so here's the first glimpse of the WGF framework. So again, this is a Chrome plugin. I was super skeptical of it. I was like, I don't want to install any more Chrome plugins, but it's actually pretty cool. You have to add even more kind of boilerplate code into the training. This would be called timeline JSON. In the workshop, I have CPU and then I have GPU timeline. Keep them separate so you can look at them separate. The picture that we have on the right is actually the GPU, and this is before the XLA fusing, right? So bottom right, you can kind of see a lot of operations or function calls there, right? And when I show the same diagram side by side, it's going to show the XLA as just one operation, which is awesome from a memory throughput standpoint. If you do, this is kind of showing, this is all timeline based, right? And showing, so you can actually see the streams in there too. So streams are actually highlighted. Mem copy it from the CPU to the GPU. That's highlighted up here. You want to minimize that, right? Or sort of batch them up. Also CPUs down there. It's kind of boring. So that would be a feed exercise. One thing, because whenever I come out and speak, I always want to pull out things that I had trouble, when I was first learning about something. I did the same thing with Spark. So this is a diagram that really hit home with me and finally helped me understand what these .meta files are, and you know, these terms, assets that you might see. Tags is pretty standard, right? Tag everything so you can search it. Yeah, we know this from like the Amazon console. We know this from Kubernetes. We know this from like lots of things. But there's this concept of a meta graph that's actually, that contains that same graph that we had talked about before. So the meta graph is more than just the graph. The meta graph also has metadata. It's common things that would travel with your graph. So if there's any lookup tables, right, like when you do the inception, when you're like predicting, when you pass in an image and it returns human readable names, that's because of a lookup table, right? That travels around with that inception model that can translate the numerical, right, like result, and say, you know, 5 is a penguin, and you know, 6 is this, or yeah, so that you're not, you know, like sitting there with your own lookup table. So that's part of the metadata, which is why you always see these like .meta files, because really these graphs by themselves need this extra metadata. Signature def is worth pointing out. It's actually a TensorFlow serving concept, but it's important to highlight why signature def is needed. The early days of TensorFlow serving, when you deployed your model, you had to know the exact name that like TensorFlow assigned to your feeds and your fetches, right? Because whenever you're doing predictions, you're feeding in data. That's typically data like JSON data, you know, or like a web request. Just picture a standard web request that has this JSON payload. You sort of unravel that payload. You feed it, and then you want the fetch, right, which is the result. And yeah, so TensorFlow internally does a lot of munging and things like that, and especially inside of notebooks, when sometimes you might have multiple graphs loaded that you don't know, because maybe you've run the notebook out of sequence, maybe you started in the middle and then went to lunch, came back, and started from the top again. And so what would happen is people were deploying, and from run to run, those sort of internal names that you didn't really have much control over changed. And you would deploy the model, and your JSON service or your TensorFlow service, like TensorFlow serving service, was expecting to like pass it in under one name, and it was blowing up. So signature def is this logical mapping now. So you can keep the logical name the same for your feeds and your fetches, so that your custom code can still deal with those. And then upon deployment of that model, there's these utilities within TensorFlow to actually build those maps. And it's like literally just a map of the simple input to x underscore observed :0, whatever TensorFlow decides to do. So one thing to also note here, and actually I think it's on the next slide. So a graph is static, right? Like when you build this graph, this is a static concept. That graph kind of lives on its own, and then what you're doing is training variables, like training weights, training parameters, like whatever you want to call them, and those get stored separately. And the reason for this is you want to be able to pull up that same model and then continue to train. So you would start up again, you would restore the model, you would like pull up the graph, you would like initialize it with the current checkpoint, like the latest checkpoint. And yeah, let's say maybe you have this new crop of images that just came in that you want to continue training. Or you can grab an existing model, right? This is what people do with images typically. They'll grab like the inception model that Google has trained on millions and millions of images, and now they want to pipe in like their own domain-specific images, right? So bathrooms and like vacation homes and views and like things specific to like hotels.com. So that's a whole other concept called transfer learning that is a bit more complicated than the way I'm describing it. But like you're essentially transferring someone else's work, right? Because that model has really picked up edges and can and so with a very small amount of your own data, right? Like you can actually train it, right? Because you have a picture that is a beach. You're going to train it with this model. You're just going to restore those weights and this whole architecture. And it's going to forward prop through. It's going to see that it didn't get it right. It's going to then back prop and then train on your specific data, but reusing, transferring all of that knowledge from the original. One thing to note too is that at training time, these stay variables because they can continue to change. But when it's time to actually serve the model to do just the forward prop, just to do the prediction, you really have to convert these variables into constants. So this is when you actually combine the graph and the latest set of learned weights or learned variables. That becomes one unit, and then that's what you actually deploy out to TensorFlow serving. And the whole purpose there is that you are not doing any back prop. So yeah, these values are not going to change. It's kind of what I just said. Variables are checkpointed separately. Graph def saved as is. And it's all part of a TensorFlow session, just like you'd have a Spark session, something like that, right? Want to point out that there is this TensorFlow debugger. It's like the most advanced command line debugger I've ever seen. It has mouse support, and it probably supports light pens, and, something crazy, but it's pretty cool. So this is what you could do to actually, if there's super obscure things happening, right, like vanishing gradients, right, like things like that, where you can't really tell from TensorBoard itself. It's too coarse-grained. It's only logging every 1,000 steps or every 20 minutes or something like that to TensorBoard because of the throughput. This is like an example where you can actually step in and dump out the current value of your tensors and sort of see that whole flow that's happening. You have total control to kind of get in there. Yeah. So this is all. The one thing about a lot of these things I'm showing here is that this has to get built from source. When you just do pip install TensorFlow, you don't get most of this stuff, right? The advanced stuff. And yeah, this is the part that takes 9 hours to build and very, very brittle because they don't have a lot of continuous integration on these sort of edge cases, right? They have sort of the mainline pip install just to keep the common people like us happy, but when you start straying. I'm going to zip through distributed TensorFlow. I like this diagram. This actually generalizes well. The next slide is actually true distributed. And there's a couple small change or big differences between single node and multi-node, but the concept is the same. Here we have a CPU that's sort of acting like that parameter server, right, that I mentioned before. That's storing the variables that we're learning, and each GPU gets the same copy of the model, and hopefully that model fits into each GPU's RAM, which is about 12 gig right now each. So yeah, this is sort of data parallel. This is most similar to how we think of Spark doing training, where it's dividing up a data set into multiple partitions. Here it's multiple GPUs. Each GPU sees just part of the data, and what it's doing is figuring out for all of the variables that it is responsible for in this current run that it's seeing in this data. It's going to make hints, for the backprop as to which way, based on error, right? How far off was I from the answer key, which is provided at training time. And each GPU then makes a recommendation, and so this is where some of the stochastic, randomness comes into play. Is you want each GPU to be seeing different data. You want random data to be coming in, and then each GPU then reports to the CPU for all the variables that the GPU knows about from that particular mini batch. Then the CPU averages or adds or does some sort of aggregation that's consistent with every step. Then it updates the sort of that master value for those variables, and then it broadcasts up to each GPU. So yeah, this is called data parallel training. This generalizes. Oh yeah, one thing to note is that there's a natural synchronization barrier here where the CPU can't do the averaging until it gets the answer from all GPUs. And so this is usually okay on a multi-GPU system, single node. This doesn't always work in a really true distributed sense. There's a lot of things that could slow down certain machines, right? There's a lot of network issues. And what you don't want to do is halt training because you're waiting for 64 nodes to actually report. And so that's where you do asynchronous updates. So this is synchronous, but yeah, you also want to do asynchronous as well in certain cases. The problem with the async is that that CPU, or in this case the parameter server, is broadcasting out values that are most likely out of date, and you can potentially not converge at all if things get really wonky. So just as long as you're sort of handling this case and not letting latencies really affect training, you would just kill the node at that point and spin up a new one and keep training. But yeah, you have to be careful with the async. So yeah, this is one thing here is, so this is single node, multiple GPUs. There's GPU 0, GPU 1. That's two separate workers, two separate physical nodes, and each one has just a single GPU. So this is single node, that's multi-node, and you write the same code, you probably build the same graph, and then TensorFlow sticks in the send and the receive. And it's all gRPC, of course, right? Yeah, Google loves gRPC and protobufs, which is super annoying when you're trying to build a JSON HTTP layer. One really cool optimization, and this happens in Spark quite a bit as well too. That this came in Spark 1.2 or 1.3. This concept of if each node has multiple GPUs, instead of each GPU reporting to the parameter server separate, there's this pre-aggregation that's happening on each worker node. And so so each node knows of its GPUs. It sort of pre-aggregates. It'll pre-average and then just send one hint to the parameter server so that the communication is minimized to just owe the number of workers, not the number of GPUs. Asynchronous, synchronous, mentioned that. Data parallel. If you do have a case where your model can't fit into one single GPU, right, which is pretty rare for most of us, this is where you have to switch over to model parallel training. So all the training that we typically think of, Spark and all that, is data parallel, MapReduce data parallel. This is where stuff gets crazy, because if you don't split up your graph in an intelligent manner, so there's going to be a lot of excess inter-node communication, right? So there's kind of tricks and things. It's like typical graph processing, basically, where you're trying to kind of split it up and figure out if you're going to go partition, or if you're going to do edge partitioning or node partitioning, that kind of stuff. So not a lot of people have to deal with this kind of thing. And as GPU RAM gets larger and larger, hopefully you won't have to deal with it. But it's sort of the sort of inverse of the data parallel, where now each GPU sees all of the data, but it's only responsible for part of the model. Right? Whereas with data parallel, each GPU only saw part of the data, but it had the full model. I'm going to be blunt here. Distributed TensorFlow is really, really difficult. There's all kinds of tricks and weird things. The craziest one I was playing with last night, trying to prepare for my talk tomorrow. They have these, was it Jinja or something? These templates that you can generate. It's just all this crazy this crazy boilerplate. So this is obviously one of the areas where Google Cloud ML is going to shine, is that you don't have to do your own distributed TensorFlow. All you do is upload your model and point it to, I guess they assume the Google storage endpoint, and it will handle all the distribution. Trying to do your own distributed TensorFlow gets really wonky. There's a lot of failure cases. Just like any distributed system, like Spark, if the Spark master goes down, you're hosed, you have to have Zookeeper involved, and like no one ever talks about that because it's sort of batch, and if it goes down, you just kick it in the morning or whatever. And so similarly, TensorFlow has this concept of like a chief worker that's responsible. So here we have 3 workers. Those are the guys, right, that are actually doing the like back propagation and sort of the like heavy lifting. So that's where like GPUs typically sit. You have one chief that's typically 0 because you're always guaranteed that there's going to be a 0. Yeah, at least one node. And then you have your like parameter servers up there that are distributed as well. So these parameter servers are their own cluster, and it's the chief's like responsibility to actually keep an eye on the health of all these other nodes. So also the chief is responsible for triggering checkpoints. When the cluster does have to recover, everyone waits on the chief for it to get its shit together before those start to ask for like, more data to continue training. Right, but essentially there's so many failure cases that will completely halt training that this is tricky. Yeah, oh, that right there first. Yeah. Yeah. Right. Yeah, yeah. And actually, I just got asked this question a couple weeks ago, or actually last week. Like, where is data locality, right? Yeah, so we all love data locality. That's one of the good things about MapReduce and Spark, is that compute is actually happening on the same node as the partition. That was sort of a generalization of the question you're asking. This is where things, these like goofy frameworks like tensor frames and things like that come into play, where like you're essentially treating TensorFlow just like a library that gets distributed to each Spark worker, and Spark is doing all the distribution. So that's one way to do it. I still haven't seen anyone actually use tensor frames in production on like anything serious. And then the other one is, was it TensorFlow on Spark that came out by the Yahoo guys? Like maybe, actually it was Valentine's Day, yeah. Yeah, I don't know why I remember that. I guess I had nothing else to do on Valentine's Day except celebrate, and like read papers. But that's doing all of these goofy things. I mean, it's a great framework, and comes out of Yahoo. Yeah, they did a really good job with it. But like essentially, it's bypassing the TensorFlow distribution. Actually, I don't think that's totally true with the TensorFlow on Spark. I have to go back and reread it. But yeah, there's a great blog post where I think it's actually using the best. It's making distributed TensorFlow easier, but it's still giving you data locality. Now, one thing about data locality, I will mention, I come from like the Netflix thinking, where so Netflix kind of pioneered using S3 and not HDFS, right? Like when I was there was not a single HDFS cluster. I think now there is, just for like temporary data. So yeah, they're using this super fault tolerant like distributed file system for things that aren't that important. Just total Netflix thing to do. But so in their own performance tests, because these workloads are so compute bound, right? Like data locality really doesn't matter, right? Or it might impact you just a small amount. And the like benefits of kind of not having to deal with that layer and just calling into S3 and saying, hey, so taking that like network transfer isn't that big of a deal relative to the types of like machine learning and AI and stuff. Yeah.
What's inside the memory of the GPU? So if it's just a bunch of weights and a graph, that shouldn't take that much.
Yeah, and actually, it's not even the weights typically. So it's kind of the temporary. I keep mentioning it's providing hints, right, which are called gradients, and it's just storing those gradients, which are small numbers relative to, and each GPU only sees a mini batch of data, and not all of the variables in the entire system have come through in that batch. So yeah, it's just sort of temporary data that it then synchronizes to the parameter server, and the parameter server is CPU-based, huge cluster, and has a lot of memory. Yeah, I mean, I haven't really seen graphs that are larger than 2 or 3 gigs, something like that. But like typically, your graph isn't that big. I mean, these are huge graphs. Typically, these this is NLP type things. This is speech recognition and things like that. These graphs, right? Like the word embeddings, can start to get big and things like that. So here's a bunch of failure cases. Coming from Netflix, I just naturally think of failure. That's probably why I'm still single. I go straight to the failure case and not think of the happy path. But one thing to make this easier, they've built in this, so any modern distributed TensorFlow that you're doing on your own, you should be using this monitored training session. There's also hooks in there at like different points and like different scenario, checkpointing hooks and things like that. Of course, this is where they plug Kubernetes, but you can also use Mesos. And then always checkpoint to persistent storage. Parameter servers can be sharded. This is actually that slide. I had mentioned this earlier where you have one cluster for training. I have to kind of clean up this image. It's not very obvious, but you've got one huge cluster that's training. That's then checkpointing out to disk, and then HDFS, and then there's this sort of score smaller cluster that's picking up these checkpoint files and then validating with data that has not yet been seen and will not be seen by the training cluster. Newer things coming out. This is actually kind of part of, like a little bit creeping into Keras. If you guys remember when TensorFlow first came out, there were like 25 different high-level APIs. There was even 2 named the exact same thing, TF-Learn. And Google had their own TF-Learn, and then there was someone else that had TF-Learn, and no one even knew. People within Google didn't even know about the other one, and they would go to that other one thinking it was their own, right? And then they would be writing code, and they get code reviewed, and they're like, what is this random framework that has the exact same name? So the quick history, Keras is pretty much one, I guess you could say. It's the one that you hear most about. Keras started off as kind of a high-level API that sat on top of Theano and Caffe, and you didn't have to really think about the internals, and you could swap in. So just like any other high-level API, it's sort of bounded by the least common denominator, features for each framework. Google smartly made a job offer to the creator of Keras, François Chalet or something like that. I should probably learn how to say his name because he comes up all the time. And they are now building native integration from Keras that's going to take advantage of the like TensorFlow distribution, right, like a lot of the native things to TensorFlow. So yeah, that's good news. Is that these like higher level libraries, or this particular high level library, will extend and make some of the distributed TensorFlow stuff easy. And of course, they're making sure. Oh, and so these 2 classes came out. There's the experiment class and then the estimator class. Kind of came around the same time as like the generic, like the example class I mentioned earlier. These just so happen to be concepts that Google Cloud ML is using. That's obviously not a surprise, right? Like I saw Databricks do this, where they would, this is like any company, Cloudera, like these guys, they kind of steer the open source project to fulfill product managers' wishes from customers. These concepts are all kind of converging, but like this isn't super evil because it's actually making things a lot easier for us developers. But they are kind of steering us towards experiment and then the estimator, and possibly slowly deprecate some of the older ways to do training. So. All right, here comes XLA. I'm going to breeze through this. The goal here, so if you think of like LLVM as probably the most similar, which actually the XLA uses LLVM. This is just like any sort of logical plan to physical plan type of concept. There's an intermediate representation. right, like an IR. The goal here is to improve portability. Google is very, very focused on mobile, of course, right? Yeah, they love Android. And there's tons of examples on how to get stuff working on Android. There's like out of the box, you can just run a few scripts and you can actually get a little emulator up and push it to your phone. And so this also helps TensorFlow stay flexible, stay performant. It can actually compile down natively. So they call their language HLO, High Level Optimizer. It's just like any other IR. It's sort of independent of the source and the target. And then there's other things that come in and then actually natively compile to x86, of course ARM, and the NVPTX, which is the NVIDIA. That's their version of the assembly for GPUs. JIT compiler. This is doing all the fusing, things like that, loop unrolling, constant folding. Yes, I mentioned this before. You could do it at the entire session level. You could do it where your code specifically assigns it to a device, to hints. That's actually some sample code up there. There's this magical debugger that the Google guys keep showing that no one can find in the actual open source code base, but you call dump and it'll, it's this REPL. You can put code in and then call dump and it'll actually dump out the assembly. Here it's simplifying a squared operation. This is kind of the visual version. So that was the before, where this particular GPU is doing a whole ton. And like you see here, this looks like it only has one GPU. But if you do have multiple GPUs, you typically see TensorFlow serving pick just one GPU. But because otherwise it has to transfer the data between these GPUs. And I think that's the same snippet of code I had before. That's how you instrument to generate this JSON and then install the Chrome plugin for WTF and you can visualize. This is another way to visualize what's going on beneath the covers. Some of the constant folding here, and there's like a whole page on this HLO business. Like the actual operators within HLO, the actual language definition. It's all publicly available, of course. And then there's a way to use GraphViz to visualize. Take these .dot files, convert them into JPEGs. All right, so this is where we're going to switch over to the inference optimizations. And I don't have too many slides left here, but I said 50%, but it ends up being about 70-30. Because there's a lot of cool stuff on the training side. All right, so again, this is where we have a trained model. And now what do we do with it? We can do various transformations. We could do that cool AOT stuff I was talking about, where it can figure out just the bare minimum. Let's see. So this is that TF compile that I was talking about, and it packages it up. So you give it the feed, or the feeds and the fetches that you're interested in. It's going to create a CC library, a header file, object file that you link into your app. There's a lot of examples about showing Android doing this. What's really cool about the Android stuff, and I mean, I'm just an iPhone guy, I don't really care either way, but there's so many examples because Google is so passionate, and these things tend to get fixed super quickly. If there's any build problems, things around ARM support and mobile support, they have tons of people work. So kind of gives you a glimpse on the inside of what Google's doing with TensorFlow. And then that's an example of going from the 50 meg down to the 600K, and it kind of shows what it picked up in terms of runtime needs. Graph transform tool. This is something I have a lot of demos in the notebooks and things like that you guys can run offline on your own GPU. Similar concept. You give it a feed and a fetch. There's lots of nodes that get injected by TensorFlow at training time that are completely not needed during the inference. Right? So there's things like those checkpoint. So there's checkpoint operations. Kind of an advanced topic would be dropout, right? During training, you're sort of introducing randomness by snipping connections between layers, typically 50% kind of thing, and you're just trying to introduce randomness to sort of compensate for some of the noise patterns that could get picked up by the network. So you just start to shoot connections in the head as though they're not there. Things like log summaries, for a tensor board. And yeah, so this is a case where once that graph has been trained, right? Like now, yeah, you give TensorFlow. Oh yeah, so this started off. Google purchased this guy's company out of London, I think, actually, Pete Warden, who has like one of the best blogs, by the way. Yeah, he talks about all this stuff, and he's like really good about explaining things because his background, I don't think, is in some of the. I think he has a pretty strong stats background, of course, but yeah, he just explains things really, really well, so that it flows really well. Yeah, he also blogged recently about how they treat all this crazy open source stuff. It's something I saw Databricks go through, where they had so many pull requests and so many different things. And at the same time, and yeah, so I'm sure Databricks is doing this now. They weren't doing this before, but yeah, so Google has their own internal version, right? And then yeah. So you'll see this a lot in the code. It'll be these like magic placeholders. That's like start like magic internal code, end magic internal code, and like you're not supposed to touch anything in there. And yeah, they have all these automated things. When you do submit a like pull request, it then tries to merge in its internal version into what you've done. And sometimes they actually push back and say, hey, can you move this over here? And it doesn't make any sense, but it's just to keep their sort of like translation tools flowing properly. Right? Like otherwise, it's just a complete disaster. So yeah, right. So essentially, if you give it a feed and a fetch, it's just going to go through and just completely drop nodes out completely. Now, it's similar to the like AOT, except it's not actually figuring out what's being called. It's just figuring, or physically what needs to be called, which like header files have to be imported, things like that. It's just literally figuring out. Yeah. So this isn't needed. This isn't needed. To provide that fetch, like the prediction. So yeah, things like folding in your final batch normalization. So batch normalization real quick, because we're doing mini batch, the gradient descent, each batch that comes in could have a completely wildly different distribution than the batch before. So one of the downsides of this mini batch, because yeah, so ideally you would have all the data, and you would just train on all the data, right? But of course, for super large data sets, this is why MapReduce exists, this is why Spark exists. You can't fit all that into memory. And then if you go the other extreme, you don't want to train on one single item, one single image at a time, because you're not getting enough data, and you just could never converge. So there's this concept in 2015 that there's a super good paper on this. Batch normalization should always be using this. And so essentially, every batch that comes in, it's slowly keeping track of this global mean and variance. And at the end, now, right, and it's per layer. And now, yeah. So what can happen is once the model's been trained, so TensorFlow has stored these final mean and variance values and can burn them in once, right? And just do one big matrix multiply offline, and then now that really similar like matrix multiply. That same matrix multiply doesn't have to happen on every full profit comes through. There's another cool technique that I didn't really think too much of when I first read about it, and then I actually saw it in action. It's weight rounding. So weights. I should be using the term variable here, but it's physically in the code called, or it's part of this like graph transform tool. It's called weight rounding, and the size of your actual model stays the same, but when you go to compress, right? Yeah, so now, think of a whole ton of like float 32s. It's sort of unbounded, the range. Now, if you can round, you now have a bunch of numbers that are similar to each other that, or that are the same now after this weight rounding, and you can get 70%, 75% compression. And so this is important, again, for these small devices. If you're deploying to iOS, deploying to Android, deploying to a field of sensors, things like that. One final one, and this is one that Pete Warden guy talks about quite a bit, is like quantization, typically 8-bit quantization, and I've got a picture of it here. So if you store all of your weights, right, the variables, with full FP32 precision, you have this huge, huge range. And so you basically have to store, like a whole ton of like 32-bit floats. So obviously, that's not ideal. So once you've trained the model, you now see all of the weights, and you can actually plot them, like find this distribution, and then linearly quantize down to 8 bits. So now with just 8 bits, with 256 placeholders, right, like now you can represent all of the weights that you've learned. So this is huge, huge savings in terms of model size. And this is one I've seen, like the inception model natively is like 90 megs, I think. And when you do this 8-bit quantization, it actually goes down to about 20 megs. And I mean, like that's a really, really powerful model that is down by like a fifth or a fourth or something. So this is easy breezy because you know the weights, they're fixed, right? These are like the variables. When you go to deploy it, you burn them in and push them out to TensorFlow serving. So during that like burn-in process, you can actually quantize this way. But now there's activation quantization or node quantization. And so this is, in like typical neural networks, I keep meaning to put up a slide here. You have the nodes, you have data, you've got the inputs, and then you have like a sigmoid or something to kind of squash it, so it's not unbound. And what you want to do, so ideally you want to bound those values, right? The sort of output from these activations. So like before, we've actually bound the weights, and so that was easy. But because the output of these activations depends on the like input values, which are things that are happening, from your like JSON, things like that, right? That's coming in from like these like web requests. It's not very easy to quantize because you don't have the whole distribution. So what you do is it's this step called calibration, where you pick like a representative data set. Yes, obviously that opens up a whole can of worms. What's actually representative, but with a relative small amount of data, like you can actually figure out that distribution and sort of clip and then bound it so that yes, everything gets snapped into this much smaller distribution of values, 8 bits, for example. So this requires this calibration step where you're actually doing the forward prop. So there's no back prop. You're just tracking what the outputs are from this, from each node's activation, and then plotting that and squashing it down into a smaller representation. Okay. With this advanced quantization, actually the graph gets a little bit more complicated. And in smaller data sets, for example, like this actually is slower than if you just let it, if you don't bound like the activations. And so yeah, just keep an eye on that this is not always faster. Batch normalization we spoke about. Definitely speeds up training. Oh yeah, so I'm not sure I emphasize that, but because each batch has this wildly, or could have this wildly different distribution, the model is not just learning the weights, but it's also fighting this change in like distribution. So this is going to take a lot longer to converge. You should always be using batch normalization. Final model is always better empirically. And then at the very end, you can use the graph transform tool to just do kind of an offline matrix multiply and burn in that final mean invariance. TensorFlow serving. So TensorFlow serving out of the box has really good version policies, things like that. One thing about TensorFlow serving that not a lot of people know about is it supports just generic like key value pairs. It's the hash map implementation. So there's two model serving implementations that come out of that come straight out of the box. It's like TensorFlow models, of course, and then there's this like small little one called hash map. And that's used in this case of sort of these like assets, the 5 means penguin and things like that. So it sort of comes along with that use case. But this could be used for like recommendations, right? I mean, like you can load up a whole like TensorFlow serving cluster that's just literally, when like user A like logs in to Netflix, it'll show a bunch of recommendations, things like that. Versions. TensorFlow serving always tries typically to load the latest or highest version. So unfortunately, version numbers in TensorFlow serving it must be integers, must be numeric. For some of the advanced serving like use cases that like we do at like Pipeline IO, we're always trying to use GitHub hash, like Git hashes, things like that, so you can always track everything through the system. It's not as easy with TensorFlow serving, not unless you actually build your own, which we're starting to do. We're kind of waiting for other people to do it, but so yeah, there's different version policies. The most recent version of TensorFlow serving actually has some more advanced kind of testing capabilities and A/B testing, things like that. So like you can actually have multiple versions of the same model or actually different models running at the same time from a single process. I don't recommend it that way because different models have different like CPU utilization characteristics, GPU characteristics, memory. Yes, I always like to keep the same model, just one single model per deployment. Yeah, there's the hash map thing. Of course, one thing too that like comes out of the box is this. You have a slide on it. Concept or these dials that you can actually, based on your use case, you could switch from low latency to high throughput. You can optimize, right? Like, yeah. And so the way TensorFlow does this is with request batching. Yes, I have a picture on that here in a sec, but that's one of the features I enjoy the most. It helps out at super high throughput. Also, these version policies. Yeah, this is the A/B testing. But when you do upload a new version, right, which is literally just dropping it into a subfolder. So you start TensorFlow serving, and when you start up the process, you point it at a parent directory. And then any subdirectory that has a higher number, that's the one that then gets picked up and gets swapped in. And when you do deploy the new one, and of course you can do it with HDFS now, as of just a month ago, it will drain, right, like and sort of gracefully tear down the old model and then start serving that new one. But like again, yes, I don't like the mutable like model deployment strategy. I like single Docker image, single model, trackable completely through your system, tied back, but it's definitely supported. Yeah, there's a bunch of different request batching strategies. Uses gRPC. Here's where you see the example thing coming into play. I had a whole conversation with someone one time about TensorFlow's examples, and they thought I was talking about the demo folders and the example folder and like all the different. And for some reason, we were able to maintain like a 10-minute conversation about two completely different concepts, which shows, yeah, one of us or both of us weren't really paying attention. But the first version of TensorFlow serving just had this generic predict, and it would just take tensors and it would get tensors back, your feeds and your fetches. They've since added first class classify that like comes along with this TF example, where it gives you the actual label and scores. Kind of adding typing instead of just like generic tuples of tensors coming back kind of thing. And then there's the regression as well. Pretty basic stuff. There's that signature. This is where you do the logical to physical mapping, right? So, yeah, so X observed is what my serving code will always expect is going to be there. But when I go to deploy the model, I physically cannot deploy the model. Well, actually, I guess, I don't know if you can now with the newer versions. I've always just used this since it came out. But there's these utilities to take that tensor and figure out the gobbledygooked name which is pretty similar, just might have a :0 or something, or :6 or whatever, depending on what's going on in like the rest of your program at that time. And then it's going to physically do the mapping, and then that gets burned in, and that travels along with the, that graph as part of the metadata, as part of the metagraph. I need to add some more to the slide. Multi-headed inference, this is huge. For me, I didn't really understand why it was there or why it was coming. It actually just, I think, dropped as of TensorFlow 1.1 or 1.2. But then you start to see like more advanced models where we're starting to now ensemble, and instead of just getting one answer back from this forward prop, right, like just getting like the actual classification, this is a penguin, but now you also want to capture that last activation layer, right? That's typically like a softmax distribution, and you could take those numeric values and now plug them into another model. So like you're essentially, with multi-headed inference, you pass in one set of data and can get multiple answers. And this is now becoming a feature engineering, right? So like you're not only getting one answer from one model, but now you can actually use this model to then engineer features for other models or like ensembles. So of course it's just overall super sweet. And only one prop through instead of making multiple calls to multiple models to basically get the same data. Just a couple more slides here. Some people, including us at Pipeline, actually went down the route of building our own TensorFlow serving model or server. The thinking was we saw TensorFlow come on the scene. Now has 60,000 GitHub stars for like whatever that's worth, but it's huge. And you look at core TensorFlow serving. That to me is probably one. So there's Tensor Board, right, which gives you insight during training, and the fact that TensorFlow serving came out of the box from I think it was day one actually with like TensorFlow. So there's not just a way to train and have insight into your training, but now you can also deploy the models. This is huge, right? So yeah, to me, this is one of the reasons that really TensorFlow is really catching on here. And so we saw TensorFlow serving only has 1,000 stars. Even today, it only has 1,200 or something like that. And so there's this gap, and I typically only see the same handful of people from Google contributing to TensorFlow serving, and so we started going down this route. Well, let's build our own. Let's like bring in the Netflix circuit breakers and all the cool sort of high scale stuff that Google may or may not get around to. We're starting to like design it out, and then one day there was like a huge I think it was a 900 file commit from Google, and it just had a label saying finally open sourcing the experimentation framework or something. And so this was the other aspect, so not just like the like high availability and fallbacks, but also some of these more complex A/B testing and like multi-arm bandit, things like that. So yeah, this is a case where we could start building it, and then all of a sudden Google's going to have it. This is also a place where we think CloudML is going, or because of CloudML, they're going to hold features back, right? So they're going to make it really easy through the CloudML command line and through REST API and through the console to manage experiments, but they're not really motivated to make it easy for like the open source. So, but yeah, who knows? They've contributed quite a bit so far. So also people, so yeah, they finally, after a bunch of prodding, made the TensorFlow serving core just a single snippet. It's got its own .h, and just basically you create your own model server, pass it that server core, and just call create or run or whatever, and now you have TensorFlow serving that you can embed into anything and wrap anything. So actually, I just saw Intel is working on that JSON to gRPC and HTTP, or yeah, JSON to protobuf and HTTP to the whole like gRPC protobuf to HTTP JSON thing. Yeah, so like the Intel group, I guess, yeah, they finally just got kind of tired of waiting for it, or something, and so waiting for that to drop. What's next? I think this is pretty much it here. Yep, 10 more slides, but yeah, they're fast. Request batching, so this is that concept I love. This was out of the box day one from TensorFlow Serving, where you can group. So the green, yeah, so at like the end of the day, basically, it's just a bunch of like matrix multiplies that are being sent into TensorFlow Serving. TensorFlow Serving is going to pass it to the GPU. And instead of passing, so that bright green, yellow thing, whatever it is, that's coming from one client device, maybe in South America. And blue, yeah, so that's another one from Melbourne or something. These happen to end up on the same TensorFlow Serving instance, the same process. And because we've turned on the request batching, we're telling TensorFlow Serving, wait 10 milliseconds or 500 microseconds or something, and batch up all of the requests that you get, right? Like no matter who it's from, batch them up, make one big matrix multiply. So the bottom right shows both of those from two separate clients being combined, and just from a sort of theoretical standpoint, we're just zero padding the matrix. You wouldn't do that. Normally, there's more efficient ways to do it, but pass it in. Just do one big matrix. Right? Like one big matrix multiply, and because you know the offsets and put them sort of edge to edge, when that so that response comes back, right? Like now, you can map back to the person in South America and person in Melbourne, Australia. So huge benefits. This is super beneficial for GPUs, especially when you just want to do one big transfer of memory and then one big transfer back. So the problem is at low throughput, this is not good because you will always at least have like this 10 millisecond sort of batch size to deal with, even if it's just a few calls. Here's some advanced batch scheduling. The big thing is if you do have sort of a mixed CPU, GPU, I/O bound things coming into TensorFlow Serving, this is where you would start to get tune and play with some of these different schedulers. I say just avoid all this and stick with the homogeneous, so that each TensorFlow Serving instance is just dealing with classifications, is just dealing with regressions, or hash map lookups, whatever it needs to do. But when you start to mix things, that's where things get troublesome, and we have ways to work around this now. Yeah. I think that's it. First thing, yeah.
In the future, do you think you'll be able to just go to the market and buy a model, just buy one of the slide and one of the other figures, and just load those load pictures of each and put them together and have something that can identify any scenario in the future?
Yeah, I mean, there's a lot of those data sets now. Yes, I was talking to Matt about specifically for this use case. I think it's MIT has Places data set, it's called, and it's been trained on a whole ton of beach scenes and yeah.
But the model, not the data set.
No. They've. Do they have TensorFlow? Yeah, I haven't actually looked at those links since I first sent them to you. Yeah, but things like the inception model. So, what's confusing is they've been trained on a lot of data, but you don't necessarily need. Actually, I think in the Places case, it is the data set with the labeled data, and then you can train with TensorFlow. But what you want is the actual trained model, the actual binary, and then you can do transfer learning.
So the thing we found is that you take Inception v3 as far as Vision API, that works well, but sort of core concepts, it really struggles on conceptual things like did this image inspire me? Quite properly. Terrible about the use case. And that's where the name specific information comes in. And we train that. We haven't trained Places, maybe we should. Conversations we have, I guess. You need the many specific things for that to work. This is so far.
I'm disconnecting here. I'm actually going through my phone because I couldn't
Is that how it is?
I think the guest network wasn't letting me go out on a different port, a weird port, which I see from time to time, but yeah. I was going to show you guys some of the GPU stuff. One quick note is TensorFlow tries to use as much of the GPU as possible, and this is something you have to always fight. So this is like another case where you want to try to avoid multi-tenant GPU usage. It's not like CPUs and CPU memory. TensorFlow, when it starts up, and especially TensorFlow serving, you have zero control over like what percentage, what fraction. On the training side, like you could say, like when you first create your TensorFlow session, you can pass in, just take a 0.1 of the GPU or something like that. That way you can kind of have multiple notebooks using it. But yeah, TensorFlow serving, when it's, in fact, I think that's an open like GitHub issue. Is there's a way to do it, but TensorFlow serving team has to expose it. So there has to be a community to actually create. It's just like a few lines of code and a ton of tests and a ton of documentation. But yeah, GPUs are fun. Yeah, check out the CUDA examples and like Numba. Do you guys use Numba? It's a drop-in replacement for NumPy built by the Anaconda guys, which actually HomeAway import. Kurt is an ex Anaconda guy knows. Yeah, I think he wrote a book on Python, right? Or I flipped through it. I was like, holy shit. I've got a lot more respect for Python these days than I did even just a year ago. I didn't realize how much you actually do have to think about C and all of this, like SciPy and all that stuff. That shit's been compiled. That's already native in C, so you don't really think about that. But Numba takes it one step further and has the same constructs, but actually builds CUDA kernels that you can cover. So it's not just C, native, CPU, assembly, but it's actually generating TX GPU assembly. So, check it out. Thanks for staying.
More questions?
Yeah.
That's the question. I mean, as I understand, TensorFlow is working with optimization, simultaneous prediction.
Okay.
In analyzing this data, so with the amount of data we can say, which of these two options does benefit in this type of approach? And second question, do you have any experience on images, something like images analyzed by TensorFlow?
I'm just talking to my buddy who works for the company Esri, ESRI. He's just now starting to get into TensorFlow, and he was at the GPU Tech Conference. He was going to every hands-on session. I barely got to see him. What was the first question again? The answer to the second is I don't have much experience in the satellite stuff. My favorite thing that it's kind of the colloquial thing that you read about a lot is the tank example. It's on Wikipedia and everything, but I guess the U.S. government or something had this data set. They were trying to differentiate between tanks and trees, right? And it just so happens that the day that they went out and took pictures of tanks, it was cloudy. And the day that they went out and took pictures of trees, it was sunny. And so that was actually dominating the predictions, was those parts of the images. And so they were getting horrible accuracy on it, just because of it. But what was the next question there?
It's the balance between optimization and prediction.
And yeah, so by optimization, you mean, so there's predictive optimization, right? Which that would be accuracy and that kind of thing. And then versus performance, the prediction performance. Yeah, I mean, that just depends on your SLAs. What's funny is when I talk to people about deep learning still, and their use cases, it's all still batch, like for the most part. So, like we're talking about this in San Francisco, yeah, like places like Netflix that really depend on these recommendations and things like search and like the ability to score within tens of like milliseconds and sort of augment just traditional Elasticsearch type, TF-IDF type things. I see it a lot in media, of course, but yeah, it just depends on your, like, some of the, because, yeah, so one case I've seen more than once is, and like this ties into some of the experimentation framework that we started to build and are still building now on top of the TensorFlow serving core, is you have the first version of the model goes out and maybe it's 5 layers deep and you're now scoring, maybe 70 milliseconds or something like that. And then the data scientist is like, wait a minute, like I have like another 100 milliseconds I can play with. Maybe 200 milliseconds is the particular SLA. So now they go and they build a 50-layer deep model, and now they have great accuracy. Maybe it doesn't generalize well or whatever, but let's just put it out there and see. And then now all of a sudden you have like 400 milliseconds. So yes, I always like the approach where give the data scientists more freedom to deploy and see their failures or their knobs, which knobs are steering things, and right, because like you don't really know until you actually put it out there and get it.
I guess in our use case is, can you try and put a score on speed? So like for some customers who are doing very, very complex searches, it's actually valuable when you're a little bit slower, but much more complete result. The vast majority of customers want things incredibly fast. We might trade off a little bit of accuracy and complexity for super speed. If you're a customer using a 2G connection in Azure, we have to be incredibly fast, and the bandwidth is an issue. It's the use case, the user's context. So for an our use case, there's not a one-size-fits-all. You have to target.
Yeah.
Any experience with Google's TensorFlow hardware?
Oh, the TPUs. Yeah, those come up all the time. Yeah, you probably know more than I do at this point.
We haven't yet, we're about to.
Yeah.
Do you know if any of these tools work in the TPU, or it has to be?
I mean, yeah, Google's using them, right, for their own. And sorry? Yeah, totally.
I heard it's 10% on a P100 operational in random conference. One would know that.
Oh, was it?
Right, so Google sending it to the next, uplift,
And so the guys the main engineers behind the TPUs actually just left Google and are pursuing a TPU-like startup. Because I guess the big sort of downside is that the public doesn't have access to them. Cloud ML, I'm sure will. It's going to be an upside, right? To use Cloud ML. One thing I've been talking, I spent a lot of time with the NVIDIA guys. Actually, one of our recent meetups that's on the San Francisco chapter, we had this guy come in from the TensorRT team, and TensorRT is their kind of TensorFlow serving, but it's highly optimized, obviously, for their own GPU, and they have an intermediate binding between Cafe. They're now coming out with a TensorFlow one, I think, in the next month or two. So it's basically, think of it like the graph transform tool. You train the model, and it's fine. That can take forever. It doesn't matter. Because this team is focused on the actual inference side of things. So they have all this quantization stuff down. They have tons of tools to do that. But then there's a step where you take your TensorFlow model or your Cafe model, Piano model, pipe it through this post-processing, post-training step, and then it's going to generate PTX that's specific. And yeah, so now the NVIDIA folks have those like Tensor Cores, which they're heavily optimized for. So they didn't do a very good job marketing TensorRT initially. But like again, I think training with GPUs is where everyone thinks, but GPUs and Tensor Cores and things like that on the inference side is super important. Yeah.
I have two questions for you. So I remember a discussion with you a couple of months back where you mentioned that in current form of TensorFlow serving, there is some issue regarding request queuing up and there is no backend support.
Yeah.
So what's the situation with that right now? Now basically, the second question.
Yeah.
For companies like us, right? So TensorFlow is something which is new. Right? We already have models which are PML, SparkML. What's your thought about productionizing them?
Yeah.
For example, I recently did a POC on MVP, and the results were pretty good. Right? So
it's still trying.
We're still trying, but yeah, the results were quite promising. So I just want to know what your views on it, because I've read on forums who are very critical about MVP results. So
I'm super critical. Yeah, and then Databricks now has their own.
They have their own DBML.
Which I paid attention to the last webinar, and I took a screenshot of where they posted on BinTray or something. And so, yeah, I mean, I like the whole JPMML stuff. The first question, the TensorFlow serving. Yeah, I totally remember this conversation. That was, I think that actually ended up being my bug, where I was opening up a new, how did that work? Right, it reminded me of when I was first doing netting programming, where you have channels and all these weird concepts, and you're like, what, I just want to open a connection, get persistent connection, get pass in stuff, and get data back. So I was doing something like that, where I was always opening up a new connection and not cleaning it up. When really you just open up a channel and then you pass the data in. So that was totally my fault. I saw it happen; it was consistently happening. So I just assumed it was a bug, but it was a user bug. Yeah, we're spending a lot of time. So the latest Pipeline IO has Scikit-Learn support that's not PMML based, right? So you can actually upload, and it's like a Tornado server. Yeah, I've been working with Kurt heavily to sort of optimize that. Performance isn't great, I mean, it's, but one thing I didn't realize, and so this is where I've gained more respect for Python, is a lot of the code paths, especially for this type of workload, is fully optimized, right? It's compile down, you can compile it for the hardware, that kind of thing. Yeah, I was always affected by the GIL, and I just kind of wrote off Python as not being scalable, but when you're doing these type of compute workloads, the GIL isn't really a factor, right? You can do I/O, you can do the sort of heavy compute stuff, in parallel. So, but yeah, I mean, I like the PMML stuff. It's funny because I've since de-emphasized the PMML stuff, on the website and on, in talking with people, because the first thing people say is PMML is horrible, blah blah blah. And so now I flip it and say, well, do you want to deploy Spark models? And they say yes. And then I say, just forget about how it's being done. Just know that you can upload a Spark file, and something's going to happen. If it gets converted into TensorRT, if it gets converted into something, but just know that once you upload it, it's going to return a URL, and then you can hit it. I mean, I've done tons of load testing. In fact, load testing is actually part of our command line tool now. You can, it fires up a bunch of Python processes and pounds the service just so that you kind of have a rough idea when you do deploy the model for the first time. You don't have to go through this whole, huge load testing framework. You can just run it, and it's either slower than it was before or it's faster than it was before. You have kind of a general sort of intuition. So, and that's some of the best Java code I've ever seen is the JPML. got database. Oh, the N-leaves. Oh, I'm super. I actually just. Yeah, those guys hate me suddenly. Yeah, I rip on them all the time. It's just they're building another PML, except it's JSON and protobuf or something. The latest, and I picked this up from a couple sources, but there is a public source on this. They spoke at a meetup in San Francisco. I was here actually, I think, when they spoke. They're shifting more towards like embedded devices and Rust, and I mean, I think this is turned off. Oh, no, it's not, but yeah, I can edit it later. They're making, in my opinion, every single wrong decision possible that a startup can make. They're incurring a whole ton of technical debt. They're like basically rebuilding a layer that nobody likes in the PML, except and yeah, they're just, I don't know, I just don't understand. And so my buddy wanted me to help advise them, and these guys are just going to do their own thing. Yeah. So now they hate me. But yeah, they also have someone from Databricks that's like one of their advisors, and like it's the same decisions Databricks does, right? They have their own notebook, they have their own scheduler, they've built a whole ton of tech debt. And, that's hard to recover from. I mean, yeah, they don't want to take you so far. Right? That's my opinion.
So one last question.
Sorry? So what's the solution? Consulting.
yeah, totally. Yeah, man. I don't know. I mean, I think it's because like those guys at this. In fact, I think they're speaking at Spark Summit. They didn't speak at the last one, so I thought maybe they got bumped by Databricks, but they're back in speaking, and they get asked at every single conference, like, why are you doing this? Like, I don't even want to use standards that have been around for 25 years. Why would I want to use, standards by 25-year-olds? This is where the grumpy old Chris comes into play. And they live in LA. Like, really? Like their like bio always says things about them surfing. And, come on, guys, get off the surfboard. Back on the keyboard. Yeah, no, I mean there's a lot going on. Yeah, and I think one of the guys is migrating up. He's doing Airbnb.
Cool. Thanks, Chris. Thanks everyone for coming. And yeah.
Right on. Thanks for having me. Sweet.
Thanks everyone.
Yeah, you can skip my talk. You've seen it twice now.
Just 3 times.
Oh yeah, do you need any free passes for Saturday? Yeah, I'm doing like another webinar.
Yeah, we should.
That's on the time zone.
Yeah, we should.
I can get you there. Sure. Oh. Hello. Yes, I love that shirt. I've got one that says Joyent. Yeah, because like Joyent is a cloud company. And it's got the same logo, Joyent Division.
Sorry, I don't hear you. Now I can hear you. You were saying about the t-shirt?
Sorry?
Did you were saying about the t-shirt?
Yeah, the shirt. Yeah, like my buddy has that shirt. But it says Joyent. It says a company name, and they're like a competitor to Amazon. But I don't think anyone uses it.
It's your contact because
yeah.
Do you have something in your long now?